Here's the question that I asked during the first half of this video lecture, and if you did this on Moodle, then you were presented with several options. And hopefully you realize that this is just like every time you do work on anything, you are converting chemical energy into whatever other forms of energy you're producing in your environment. And so our correct energy bar chart here should show a loss in chemical energy as you consume chemical energy in your body, and a gain in electric potential energy and thermal energy. Well, Van de Graaff generators are fairly easy to understand because they're basically just an automated way of rubbing things to separate charge, but they're not really practical for everyday circuits. So let's look at what is practical, which is batteries. And we're not going to be able to get into detail about batteries because they're incredibly complicated. Some of you are going to take a chemical kinetics course where you'll learn quite a bit of the gory details of batteries. But for us, we need to just look at the basics. So typically, a battery has some positive electrode and some negative electrode, which are both immersed in some sort of a solution. Quite typically, but not always, that's an acid solution, and the positive electrode is some oxide, which is easily reduced, and the negative electrode is usually a metal. And so what happens is that the negative ions will react with the metal. As they do so, they leave their excess negative charge, in the form of free electrons, behind in the metal. At the same time, the hydrogen ions react with the oxide, and in so doing, they transport positive charge, and so the oxide or positive electrode ends up positively charged. Now there's a depletion of hydrogen ions near the positive electrode and a depletion of negative ions near the negative electrode. And so diffusion happens. Hydrogen ions are going to be transported by diffusion to where their concentration is lower, and so with the negative ions as well. And so this means that these ions are being transported against the electric field because the electrical forces would be pushing both ions in the opposite direction. And so, as always with charge separation, positive work is being done by the battery on the charges. But note that this positive work here is being done chemically. The power source of all of this is the chemical reactions going on at the electrodes. Eventually, though, the electric field is strong enough that those electrical forces will stop the diffusion. At that point, there's a stable potential difference between the electrodes, and all of the reactions stop. Left to its own devices, the battery would now remain stable in this configuration, with a potential difference between the electrodes that we call the cell potential. However, if we connect the electrodes together with a conducting wire, electrons will flow from the negative electrode to the positive electrode, and the chemical reactions will start up again, and the transport of ions by diffusion will continue. And so we get a continuous flow of charge around the circuit. Notice that the electrons moving through the wires are being moved by electrostatic forces, whereas the ions in the solution are being moved by non-electrostatic forces. So as always, there are non-electrostatic forces doing work to bring about the charge separation. But we've now given the charge a way of unseparating by flowing through the wire. And so we have set up a continuous loop or circuit of charge flow. If we think about the whole battery as our system, then the battery is moving charge against the electric field, and so this charge, which is in the system, is gaining electric potential energy. At the same time, the chemical reactions are going on to consume reactants, and so the battery is converting chemical energy into electric potential energy. In general, like any transformation where we consume source energy, like chemical energy, this is an irreversible process, and so there will be some thermal energy produced as well. However, very often in the operation of a battery, that amount of thermal energy produced is quite negligible, and so we can ignore it, in which case we can talk about it being an ideal battery. Well, it's time for an analogy that I'm going to make quite a bit of use of over the next sections in the course. And it's ski hills. What do ski hills have to do with circuits, you might ask? Well, think about a ski hill. During the upward trip, the chairlift is doing positive, non-gravitational work on the skiers. And at the same time, the Earth is doing negative gravitational work on the skiers. Then during the downward trip, as they ski down the slope, the Earth is doing positive gravitational work on the skiers. We can talk about the work per unit mass, and it would just be G delta H, right? The work to move a skier up from the bottom to the top of the ski lift would be mg delta H, and so the work per unit mass is just G delta H. And that is the same magnitude of work that the Earth then does as the skier goes back down the hill. Because, obviously, whatever height you go up as you ride the chairlift up, you must come back down exactly that same height to get back to the bottom of the chairlift as you ski down the hill. Well, now think about a simple circuit, like a battery hooked up to some load such as a light bulb. During the trip through the battery does positive non-electrostatic work on the charges. And meanwhile, because they're moving against the E field, or rather in the opposite direction of the forces that the E field exerts on them, the E field is doing negative electrostatic work. And then, during the trip through the wires and the light bulb, the E field is doing positive electrostatic work. It's just like the ski hill, except we've replaced gravitational forces with electrostatic ones. And in analogy to the work per unit mass, we can talk about the work per unit charge, but we've already seen that the potential difference, say, from point D to point A on this diagram, is just the negative of the electrostatic work per unit charge. Well, if this is an ideal battery and none of the work it's doing is ending up as thermal energy, then the electrostatic work is just the negative of the non-electrostatic work done by the battery. Notice that the work per unit charge done by the battery is not quite the same as a potential difference, because we defined potential difference as negative of the electrostatic work per unit charge. So we need to give this one another name. We call it EMF. EMF actually stands for something, but I'm not going to tell you what it stands for yet, because what it stands for tends to lead to misunderstanding. In any case, it's the non-electrostatic work per unit charge to bring about a charge separation. And so notice that it's measured in volts, because it's again joules per coulomb, so just like a potential difference. And so if we have a battery bringing charge up a potential difference of 1.5 volts, then if it's an ideal battery, then its EMF would be 1.5 volts. Note that you can talk about an EMF for something like a Van de Graaff generator as well, because it's transporting charge through a potential difference by doing non-electrostatic work, and so you can just find an EMF as the non-electrostatic work per unit charge for it as well. Back to the ski hill analogy, though, notice that again, as charge is transported, in this case from D to A through the battery, it rises through some potential difference, and it must fall back down through that exact same potential difference on its trip back around the circuit to the other end of the battery, because potential is a function of position only. Whatever the potential is at D, the charge has to get back to that potential, just as when you go up the ski lift, then to get back to the bottom of the ski hill, you have to get back to the same height above sea level that you were at when you started. A word of caution about potential difference and EMF and volts. Because EMF and potential difference have the same units, namely volts, they're both often referred to as voltage. But notice that they're not quite the same thing. One is talking about non-electrostatic work per unit charge, and the other is talking about electrostatic work per unit charge. Well, so it can lead to confusion when you call them both voltage. I will try and avoid doing that. However, it is an ingrained habit, and I may slip up and do it from time to time.